Welcome back, grade 7 and 8. In our science video today, we are going to start taking a look at the history of the atom. And so as we explore more about the history of the atom, we're going to have a couple of things that are written on the screen that signify key dates, key people, and key discoveries about the history of the atom. If I have it on the screen, please make sure that you are pausing or that you're writing that in your notes, that you are including that. As that's going to help us understand a little bit more about where we came from in our understanding of the atom to where we're at now as a continued unpacking of this wonderful thing that God is allowing us to learn a little bit more about. As scientists have done experiments to learn more and more about atoms, though, they've changed how they think about atoms. In this video, we're going to look at a timeline of different ways that scientists have pictured or imagined about over the years. Now, the first people to really talk about the idea of atoms are the ancient Greek philosopher Democritus and his teacher Leucippus. They lived about 2,500 years ago, between 4 and 500 BC. And Democritus, he said something like this. He said, imagine you have an object, like say a slice of bread, and you cut that in half. And then you take half of that and cut it in half again, and you take half of that, and so on and so forth. You get the idea. Eventually, he said, you're going to come to something that you cannot cut in half anymore. And he called these objects atomos, which means uncuttable. And it's where we get the word atom. Democritus imagined that all matter, all stuff, was made of these tiny, uncuttable particles. And he imagined that the atoms came in different sizes and different shapes. He imagined, for example, that iron atoms had hooks, which is how they could hold together so strongly. And he thought that salt atoms had spikes on them because he felt that salt tasted sharp. So Democritus was right, but people didn't really take to his ideas. Part of the reason was because around the same time, the well-known philosopher Aristotle proposed his own idea of what matter was made of. He said that different things were made of different amounts of the elements earth, water, air, fire, and even ether. And more people believed Aristotle, possibly because he was so popular already. So Democritus and Leucippus were right all along, but here's the thing. They weren't scientists. They couldn't do experiments in a laboratory to prove that they were right. And because of this, some people think that their idea, it was just kind of a lucky guess. They couldn't actually prove what they thought. So, how can you tell whether it's right or wrong? Ideas about atoms remained that way for over 2,000 years until about 1808. And in 1808, the British chemist John Dalton, who was also a school teacher, came up with the first scientific experiments that showed that matter was actually made of tiny little particles. This was kind of how John Dalton pictured atoms. He imagined them sort of like tiny little balls that arranged in different combinations to make different things. And he imagined that these atoms were indivisible, just like what Democritus had thought. You couldn't cut them into smaller pieces. Now, at first, similar to Democritus, nobody really believed Dalton, but over the course of the 1800s, more and more scientists did begin to believe what he had to say. But then in the 1900s, the early 1900s, people's ideas about atoms started to change. One of the key things causing this change was that in the late 1800s, a man by the name of J.J. Thomson discovered that atoms have electrons. And he discovered that electrons are much, much smaller than atoms. So while Dalton thought that atoms were tiny and indivisible, J.J. Thomson said, no, they're not indivisible because they're made up of tiny electrons, which are much smaller. So J.J. Thomson pictured the atom as sort of like a blueberry muffin. He called this the plum pudding model. And J.J. Thomson imagined that if you took an atom and split it open, you'd see tiny electrons stuck throughout the inside of it, just the way blueberries are stuck in the dough of a blueberry pudding or a blueberry muffin. And Thomson thought that what's the dough in blueberry muffin, that it was like a positively charged substance. So you had negatively charged electrons stuck in sort of like a positively charged dough. And together, the positive and negative charge balanced each other out. The two things balanced each other out, so the electron or the atom was considered to be electrically neutral. But the big change from Dalton's model to Thomas's model was showing that atoms weren't actually indivisible. They were made of even smaller things. He actually did some interesting experiments to show that this was the case through what's called his cathode ray tube experiment. We're going to be exploring and learning a little bit more about that later on. But it essentially involved him shooting these rays of electrons through a cathode ray tube. You can see kind of a picture of it here. And when it bounces off of a phosphor-coated plate, then it allowed it to light up. And you might say, okay, that's great and all. He's able to create a beam of light going through a tube, but how did he know that these were electrons? How did he know anything more about it? Well, he took a really, really strong magnet, and he realized that when he put the positive end of the magnet next to this, then it would bend towards the positive side. And that's because opposite charges attract. He also realized that when he put the negative side, that it bent away from the magnet because like charges repel. And so he realized that whatever was shooting through here had to have a negative charge to it. And in order for the atom to be electrically neutral, there had to be some sort of positive side in order to balance that out. Now, not too much longer, we have another man who comes on the scene, and his name is Ernest Rutherford. And Rutherford discovered that atoms actually had a nucleus. So it wasn't really like this solid structure that Thomson and previously Dalton had thought about, but Rutherford said, no, there has to be some sort of dense inner nucleus as a part of this atom. And that all the positive charge in an atom was concentrated right in its center. And that besides that, the electrons in the atom were pretty much in a big area of empty space. And so we're starting to get somewhere close to the model of an atom that we know it to be today. Now, he did this through something that was called the gold foil experiment. Now, this is a fairly complex experiment that involved shooting particles at a really, really thin sheet of gold foil. And some reflected off and most went straight through, showing that the majority of what's making up that gold foil, the majority of what makes up that atom, is empty space. But there had to be some sort of central dense nucleus because some were bouncing off. We're going to explore that a little bit more later on as well. But you'll see that we have a dense center nucleus that's positive, and so he's also credited with discovering the proton, the positive part of the atom, and that the electrons, the negative parts, had to be flying around in this blank empty space around there. So J.J. Thomson thought the positive charge, they were all distributed throughout, like dough in a muffin, but Rutherford showed that all this positive stuff was concentrated right in the center. And this is what we call the nuclear model of the atom. So the picture that we have there is an example of the nuclear model because it has a nucleus. Sometimes people also call this the Rutherford model. It kind of goes by both names. So far we've been talking a lot about the positive charge and the nucleus of an atom, but we haven't talked a lot about what's actually going on with these electrons in the atom. We've just kind of talked about how they're floating around randomly in space. Well, in 1913, another physicist comes on the scene, and his name is Niels Bohr. And he came up with his model of the atom. He reasoned that there's a nucleus in the middle, just like Rutherford had, but that electrons Instead of being randomly distributed throughout the atom, Bohr said that the electrons were sort of like planets around a sun, that they were spinning around the nucleus in circular orbits. So here's a picture of some of the electrons in the orbits that they go around in kind of a nice circular shape. Imagine that they're spinning around the nucleus in these circles. Right now, people thought Bohr's idea for the electrons made a lot of sense at first, but then in the 1920s, additional experiments showed that wasn't exactly the way electrons really moved. And a variety of physicists, particularly the physicist Erwin Schrodinger, showed that electrons weren't really spinning in orbits, but it's more like they were hyperactive flies. And they were buzzing around the atom, sketching out different kinds of shapes. It's kind of like you did a time-lapse photograph on a hyperactive fly and you saw that over a long period of time it sketched out a particular design. And whereas Bohr called these circular paths, he called them orbits. Schrodinger called the hyperactive sketchouts, he called them orbitals. So this is an example of a circular orbital, but electrons don't only make circles. It's actually a sphere because it's a circle but in 3 dimensions. So we call this the quantum mechanical model of electrons. And in the quantum mechanical model, electrons don't orbit the nucleus. They buzz around the atom, sketching out different shapes in what we call sort of an electron field. Now let's focus though on the nucleus. Because over the same amount of time and a little bit later, scientists were discovering the 2 subatomic particles that make up the nucleus, so we can refine this picture a little bit more. In 1919, Ernest Rutherford, as we've talked about previously, discovered the proton. And then in 1932, James Chadwick discovers neutrons. Interestingly enough, this actually ended up being the stepping stone to eventually cracking the code to learning a little bit more about the atomic bomb. So it was one of the things that was actually used in a very, very destructive way. But he discovered the neutron, which was actually very, very challenging to discover. Because the electron you could figure out because of how it reacted to a magnet. It's a negative charge. The proton had to be there to balance out the negative charge, but the neutron had no charge. So we're going to learn a little bit later on that the neutron actually needed to be discovered by taking a look at the atomic mass and realizing that there was something missing. But now that we have James Chadwick's discovery of the neutron, the real correct view of the quantum mechanical model shows the orbitals being sketched out by the electrons, but then also shows the subatomic particles, protons and neutrons, in the nucleus. Now, this is pretty much how we think about atoms today. But as scientists learn more and more about atoms, as they do more and more experiments, they're going to find that this model might not be exactly a perfect representation of what atoms are really like. And they're quite likely going to change this and refine it ever more. This is a work in progress. As we discover more, we refine it. We get closer and closer to what seems like it's the most accurate representation of what a model is. Now, as I've said before, the quantum mechanical model is like the really accurate way to describe a model. But the thing is with those orbitals is it can really be kind of a pain sometimes to describe simple things that atoms are doing using electron orbitals. And so a lot of times when we talk about atoms in class, I'm actually going to be using sort of a cross between the very correct quantum mechanical model and the sort of outdated Bohr model. Just because for our purposes, a lot of the simpler things we're going to talk about, the Bohr model, it works just fine. So sometimes when we draw atoms, we're going to be drawing them like this, with the proton and neutrons in the nucleus. Here we just see Mg in the nucleus, but that center part there where Mg, or the magnesium symbol is where we would draw the protons and the neutrons. And the electrons in rings, in different rings or different orbits on the outside of the atom. We're going to find thinking about the atom like this is very useful for simple tasks like talking about bonding. But keep in mind that when we're discussing atoms, they actually aren't exactly like this, and they're much more like the quantum mechanical model. So keep in mind that I am lying to you a little bit, but I'm lying to you in order to make it easier to convey some fundamental topics. So this gives us a little bit of an unpacking as to the history that led from our understanding of the atoms of just being some idea of something uncuttable to now starting to understand a little bit more about the subatomic parts. And as I've shared a little bit earlier, this is a field of science that we are still continuing to learn more about. We're even learning now that some different subatomic parts of the atom may actually be made up of other subatomic parts, and that they have different qualities to them as well. We're going to be learning over the next couple of classes how to not only understand what the importance of these electrons, protons, and neutrons are, but how to figure out the number of protons, neutrons, and electrons in a specific atom, and how we can actually draw or create some of these Bohr model diagrams for certain atoms on the periodic table. Well, that is it for today. I hope you learned a lot about the history of the atom, and I will see you again next science class.